Alright, so let's do a couple practice questions here. I didn't want to put these in the main line because it makes for a super long video. So we'll do number 1 here, and then we'll do number 2 on a second page. An ant travels 2.78 centimeters to the west, and then turns and travels 6.25 centimeters south, 40 degrees to the east. Okay, so if I'm thinking this through, I want to have enough space here for my ant to walk to the west, 2.78 centimeters, and then from that location, and I'm going to make a little X there to help keep track of things, I now have to turn south 40 degrees to the east, and 6.25 is almost 3 times bigger, so I would expect this to be a larger vector, maybe something like that. The 40 degrees goes in here, and this is 6.25 centimeters. So the value of making an accurate diagram comes out when it supports our answer. That's a really key piece. So we're going to have delta 1, delta 2, and we're going to find their components. We need to choose a positive direction. So I'm going to choose positive to the left and positive down. Might as well make our lives easy. Okay, we could do the traditional to the right and up. It would still work. So when I go to fill this in, my first vector has a positive 2.78 centimeters to the left and 0 in the y direction. My green vector here, if I break it down into its components that have to add, so we're looking at the tip to tail, I have to go down a certain amount, so that is going to be cos 40 times 6.25. So if we grab our handy dandy calculators and go cos 40 times 6.25, I should get 4.8. Okay, and then down here we would have sine 40 times 6.25. So sine 40 times 6.25, and that's 4.0 we'll say. So now if I look at this convention, down is 4.8, and it's positive because I matched up with my convention. And now I'm going to the right here, so this 4 that's going horizontally on the bottom, maybe I better scroll that up a little bit, it will be negative. Okay, and now we can sum those columns. So we have 2.78 minus 4, we're left with negative 1.22. And if we add up the y's, we have 4.8. Okay, so my resultant, and I'll do my resultant in red, starts here and finishes here. And if you look at that, I'm going back. There's the 1.22 back. Here's the 4.8 down. Okay, so these two pieces right here make up the components of the red resultant. So if we wanted to find the resultant magnitude, that is a quick Pythagorean theorem. You notice I'm not worried about the negative sign because when I square it, that will disappear. So if we go 1.22 squared plus 4.8 squared equals square root 4.95, and we could probably round that off to 5 if we wanted to. 5 centimeters. And then we need to give a direction or an angle here. So I'm going to try and find this angle up here, this theta in this corner. Okay, you can find other. I like that one because it's where I start. That's an important piece. So if I say tan theta would be 4.8 divided by 1.22, and again I'm not worried about the negative signs because I'm just working with the triangle. And I would have, oops, second function tan answer, 75.7 degrees, so let's just say 76 degrees. Okay, so now I have to communicate that as my resultant. So it would be 5 centimeters at, and now I need to give it a direction. 76 degrees isn't accurate. That's the piece inside the triangle. I have to anchor it somewhere. So I could say east 76 degrees to the south, and that would anchor it at east, turn 76 degrees to the south, and that would be my resultant for my ant. So let's go up here and check. So 5, we were pretty close, and there's the east, 76 to the south. All right, so that's the table. You can see if it's well organized, it's pretty easy to follow. Let's try the next one. A paper airplane flies 2.64 meters west, 26 degrees north, and then is caught by the wind, which causes it to travel 3.21 meters south, 12 degrees to the east. Okay, so I'm going to start my picture somewhere in here. I'll make my little X that I find helpful. And now I'm going to draw my vectors. So I have to go west, 26 degrees north. So I'm going to estimate that's something like that. Okay, and my 26 degrees is measured in here. I would then put another little X so I can measure from that. Now I have to travel 3.21 meters south, 12 degrees to the east. So this vector should be a bit longer than the other one. Maybe something like that. Okay, this is meters, so is this. And my 12 degrees is measured inside here. Okay, and now I'm going to set up my table. So I have D1, D2, the X values and the Y values for those. And I'm going to make my triangles. I may have to move this guy down. Oh, maybe not. Let's erase him for now. Let's say this is 2.64. Okay, so if I'm creating blue, if I make these vectors added tip to tail, I'm looking at the components. So I need to choose my positive convention here. So I don't think it's going to matter. So let's just do traditional. We'll go up and to the right as our positive convention. I'll slide that over here. So now we want to find, this is 26 degrees on the bottom, so this would have to be 64 degrees inside. That's one option. So now let's use that information to find our X and Y values. So we can use SOHCAHTOA, so sine 64 times 2.64, and I get, let's just say that's 2.4. If we find the Y value here, that will be cos of 64 times 2.64, and that is 1.2, let's say. Okay, so now when we go to enter these in our table, the 2.4 for the X is going against our positive convention, so it's going to be a negative, and the Y value of 1.2 is up. It's with our convention, so it stays positive. If we look at the vector for green here, creating the vectors components that add to make that resultant. There we go. So now we have 12 degrees, so we're going to go cosine 12 times 3.21, and I should get 3.1 for the Y value, and then sine of 12 times 3.21 is 0.7. Okay, when we go to put those into our table, our X value is in the positive direction, our Y value is in the negative direction, and then we're going to sum those columns. So 2.4 negative, try it again, negative 2.4 plus 0.7, should have done that in my head, negative 1.7, and then 1.2 minus the 3.1, negative 1.9. So if I look at my red resultant vector here, starting at the beginning and going to the end, the components for the red resultant vector, okay, would be negative 1.9 down and negative 1.7 back. So that actually fits. You can double check all of our work right there. To find the resultant, we're going to use our Pythagorean theorem for that right triangle. Okay, so 1.7 squared plus 1.9 squared equals second function square root answer 2.54. I'll carry 2 decimal places right now, why not? And 2.54. Let's give ourselves a little bit more room to find the angle. So I'm going to find It doesn't matter. I'm going to find this angle in here. I like to find the angle at the start because it tells me the direction to turn. So if we say tan theta is 1.7 over 1.9, we get a theta value 1.7 divided by 1.9. Second function tan answer of 41.8 degrees. And again, that's not a good enough answer just yet. We need to anchor it. So the resultant will be 2.54 meters at, okay, so now if I want to anchor this, I could say south 41.8 degrees to the west. That would work. Or I could create a bearing or other things. So there's my resultant. You'll notice it has magnitude and direction. So let's go check, see how we did. So 2.62, and they went west 49. Okay, so mostly a rounding errors. So if we compare, okay, it depends on how many decimal places we carried. So I'd say we're right on. Okay, and they measured their angle up here. Okay, so they measured from west and down. Both are correct. I would take either. Okay, I hope that helps. Thanks for tuning in.